This video is going to go through some conceptual questions that specifically cover the concepts of electric potential energy, wow, my stylus, we don't want to write very well right now. I know it's my computer's issue. And electric potential. It's important to recognize the difference between these. It's a one-word difference. So electric potential energy is different than electric potential, though they are related. So these are the main concepts that we're going to cover in these questions. The questions, many of them come from the book that we're using right now by Randall Knight. It's Physics for Scientists and Engineers, just as an FYI. So as usual, pause the video so you can read it and answer the question on your own, and then watch the solutions. So let's see if my screen will drag the question up. Okay, here is our first question. So the correct answer here is A. If we think about potential energy just in terms of gravity, we know if we have two balls and hold one higher, it's going to have more potential energy because it'll end up hitting the ground faster if we let it go. So the fact that A has farther to move in this electric field compared to B, it will have more time to accelerate and therefore will be moving faster as it hits the negative plate. So the one moving faster would have more kinetic energy, which came from potential energy. So farther distance from the plate it's going to head to gives it more potential energy. Let's look at our next question. What about this one? Correct answer here is B. For the same reason. Now, B is closer to the negative plate, but that's not the direction it will head. If they are both released from rest, they're negative, so they're going to be attracted to the positive plate and repelled by the negative plate. So B would be the one that has farther to travel. Therefore, it has more potential energy. Here is our next question. Correct answer here is C. So our equation for electric potential energy, a point charge has, because it is near another point charge, is K Q1 Q2 over R. Now, because these charges are opposite, we would put a positive in for one of them and the negative in for the other, which would give us a negative answer. We know they're attracting as they get closer and closer. R is going to get smaller, which is going to give us a bigger just absolute value, but the answer will still be negative. So it's going to get more negative. Oh, not more and more negative. And negative potential energy, again, means it's a bound system. It means they are attracted to each other. They're not going to escape each other and move away. So since energy is not a vector, more negative is a smaller number. So the potential energy will continue to get smaller, more negative, as they get closer. Here's our next question. The correct answer is A. Now, think of this like our capacitor. If we have our electric field, and I put a negative charge in here, I know it's going to go this way. It's going to move opposite the electric field because it's attracted to the positively charged plate. Now, as it moves that way, its potential energy will decrease because that potential energy will be turning into kinetic energy. But that's not what these options are talking about. They're talking about potential, not potential energy. Potential is V. Higher V to lower V. Electric field lines will always point from a higher potential towards a lower potential. That's independent of this test charge. So we take this guy out, our little electron that was free to move. Electric field lines always point from high V to low V. So since we know a negative charge wants to move towards the positive plate and will speed up that way, a negative test charge will move to a location that has a higher electric potential, whereas the potential energy of the electron would be decreasing. A positive test charge placed in here would go to the lower potential because that's how it would speed up and it would lose potential energy. This particular question is a reminder to distinguish and make sure you really learn and conceptualize the difference between potential energy and electric potential. Electric potential energy is what a charge actually has because it's in this electric field. Electric potential just is representative of where in the field we're talking about. It's independent of any test charge that might be placed in there and move. Okay, another question for you. Oh wait, that's the same question. Hold on. I apologize for the jumping around and changing of size. My computer's changing the size of questions as I pull them in. So I'm doing my best to try to get them back to the same size. Here is our next question. The correct answer is E. So even though this is labeled as 0 volts, and technically we can say the energy of the charge would be Q times 0, there is a location to go to down here that will have a negative potential energy, which is smaller than 0. So objects if allowed to move naturally, will always move to a location where their potential energy is smallest. Another way to think about this, we know electric field lines point from high potential to low. So there's got to be some sort of electric field in here that points downwards. We know a positive charge, a proton, will move with an electric field. So we know the proton is going to move down. Now, steady speed or increasing speed, well, we know as just like gravity, if I release a ball from rest, I know the ball's going to speed up. That potential energy will continue to transform into kinetic energy, and that would be true here as well. The proton, it will continue to lose its potential energy as it continues to move downwards, which means its kinetic energy is going to be increasing. Steady speed would mean there's no additional kinetic energy created, which means the potential energy would have to not change, which of course is not the case in this particular problem. Okay, we have just a few more. What about this one? Correct answer here is D. So electric field being a vector, we know the positive charge is going to create an electric field to the right, away from the positive charge. The negative charge is also going to create an electric field to the right because its electric fields point towards it. So when we add those together, the overall electric field points to the right, which of course rules out every other option. Let's explain V equals 0 though. So the electric field is a vector. It not only has a value to it, but it's also representing the direction that the force would be in if there was a positive charge there. Electric potential is analogous to height. Like with gravity, when we talk about gravitational potential energy being mgh, how high the object is, V, this voltage or electric potential, is analogous to that height. It's just where in the field. So to find the total V, we just simply need to use the equation for electric potential of a point charge, which is kq over r. These are the same but oppositely charged charges. They're the same distance because we're in the middle. Since potential is a scalar and not a vector, we're simply adding these numbers together, and that's what will add them to be 0. Now, having a potential of 0 there doesn't mean a charge placed there wouldn't go anywhere, because a charge would easily be attracted or repelled to one of the other charges. So similar to potential energy being mgy or h, and y equals 0 was arbitrary. We could choose that to be wherever we wanted. A voltage of 0 is relatively arbitrary. Now this equation, of course, gives us 0, but it doesn't mean a whole lot by itself. It depends upon whether there's other places, other locations a test charge could move to where the potential energy would be different. And it would be different if the electric potential was different. Here we have another question. The correct answer here is A. So equipotential contours or surfaces around two charges are shown. So this is implying point charges. The electric potential for a point charge is kq over r. So in the top situation, from Q out to the point where we have 80 volts, is bigger than the R in the bottom situation where we go from the charge out to the 80 volts. So 80 volts being KQ over R, oh dear. A smaller R to get to that 80 volts means a smaller charge is creating that 80 volts. And similar to the 20 volts, the smaller distance to that contour or surface means a smaller charge is creating that. The equipotential surfaces would be spherical around a point charge. This is just showing us a kind of a cross section. One last question. Let me make this a little bit bigger, if it will let me. So you can see I and F, the initial point and the final point. Correct answer is D. So work is the integral of the force with respect to displacement. Dot product means we only care about the component of the electric force parallel to the motion. So for path A, for example, here the work would be negative, but we're just looking at magnitude. So this part we would have some work done that depends upon this distance between the initial point and A. As we go this way, there is no work done because we're moving perpendicular to the electric field. Remember, electric force is Q times E. And the dot product specifically means the force has to be parallel to the displacement. Another way to think about it is going from A to final is an equipotential surface. Remember, we talked about putting a charge anywhere along a line that was parallel to the plate, and it would have the same amount of potential energy. So we're not changing the energy at all by moving the charge from A to F for final. Path B, the middle one, we're just going straight to initial and final. But in terms of components, we only care about this component, D, the one that's parallel to the first leg of A. That's what the dot product is doing, is multiplying the components of the force that's parallel to the displacement. So for path B, since we're still moving the charge the same distance D parallel to the electric field, it's requiring the same amount of work. For option C, as we go to the right, that would be what, positive work or negative? That would be negative work. Nope, that would be positive work because we would be moving in the same direction. This segment is no work. equals 0. And again, because we're not moving with the electric field, as we move back far enough to get back to point I, we're back to the same amount of energy we started with in the first place. And so a net work for this section is 0, because we're doing opposite signs up here compared to down here. So overall, the rest of the path is still this distance d. So we're still ending up at the same initial versus final in terms of equipotential surfaces. So the same amount of work would be done.